In this video, we are going to cover RAG with some advanced methods. I hope you already know about RAG, which is called Retrieval-Augmented Generation. Typical LLMs only know about their trained data. RAG is a method where AI first searches for relevant information from an external database and then uses that information to answer your question. This RAG can get relevant information, but it also have few limitations. So what are the limitations of this typical RAG? First one is poor retrieval quality. It may pull irrelevant or low quality chunks, especially if the query is vague or phrased differently than the document text. Second one is no understanding of query intent. It matches text literally, but it doesn't understand what the user truly wants. Third one is lack of caching or memory. It retrieves and regenerates every time, even for similar queries, wasting compute and time. So these are some of the limitations of naive RAG. Naive RAG is good for demos or small projects, but for real-world apps, you need enhanced RAG with caching, chunking optimization, re-ranking, query expansion, hybrid search. In this video, I will be discussing about multi-query and re-ranking, and also show a small demo of a RAG with multi-query and re-ranking. So first of all, what is multi-query? Multi-query retrieval means instead of searching with just one version of your question, we ask the same question in multiple ways, then combine all the answers. So basically, ask the same question in different ways to find more relevant answers. So benefits of this retrieval are better recall, more robust to user wording, great for open-ended or domain-specific documents. In this example, using multi-query, we create different questions using the original question. So as you can see, the original question is, what are the health benefits of apples? So the multi-query retrieval creates multiple versions of the same question. Each version finds different pieces of information from the database or document. So in the final result, the system combines all the retrieved chunks to give more complete answer than using a single query. We can make use of the LLM to create multiple queries. What is re-ranking in RAG? Re-ranking is a second filtering step in retrieval-augmented generation. After the retriever fetches some relevant document chunks, re-ranking reorders them based on how relevant each one is to your specific query. Think of it as a quality check after retrieval, ensuring the most relevant context goes to the LLM. Let's say you ask a RAG system, what are the symptoms of vitamin D deficiency? In the retrieval step, the retriever finds top 5 chunks based on vector similarity. In the re-ranking step, a CrossEncoder model checks how closely each chunk matches your question using deep semantic comparison between the query and each chunk. It gives scores like this. After re-ranking, only top 2 to 3 highest scoring chunks are passed to the LLM. So instead of noisy or generic context, the model gets more relevant data. So the answer is now more accurate and focused. So this is the architecture diagram of this RAG. First we upload the PDF and create vector embeddings and store it in the vector database, which is FAISS. When the user asks a question, we split the question into different similar questions using the LLM that running in Ollama. For each question, retrieve the answers from the vector database. Using the CrossEncoder model, re-rank the retrieved chunks, then sort by highest order and keep the top chunks. Then pass that results to the LLM with the original question. And the LLM gives the answer based on the given results. That's the overall architecture of this RAG. This RAG system uses different libraries. For front-end UI, we use Streamlit, which builds the user interface. For text processing or chunking, we use Python text splitting. This splits PDF text into chunks using word-based chunking. Embedding model. Here we use All-Mini-LM L6v2. This model converts text chunks. This model is small and fast, excellent for local RAG. Vector database. FAISS, Facebook AI Similarity Search. It stores vector embeddings of chunks and also performs nearest neighbor search. Ollama. Ollama is used to run LLMs locally. We can pull different models using Ollama. Re-ranking system. The model used is CrossEncoder model. This model takes query and context space and scores relevance. Sort, chunks by relevance, selects highest quality ones for the generator. Here, FAISS retrieves based on vector similarity, but CrossEncoder performs deeper semantic matching. In this code, when a user uploads a PDF, it extracts data from PDF, then splits the data into chunks. Using these chunks of data, it stores in the vector database. Using the user's query, LLM creates multiple query that relates to the answer and pass to the LLM. From the retrieved results, re-rank those results, then those results will be passed to the LLM for response. Then find the most relevant chunks from the PDF using multi-query search. Use a re-ranking model to sort the retrieved chunks by how relevant they truly are. Send the best chunks plus the user question to the LLM to generate the final answer. Retrieve context multi-query. This function takes the user's question, rewrites it in a few different ways using an AI model, and then uses all these versions to search the PDF's vector database. Each rewritten question helps find more relevant text chunks from the PDF. It then collects all the useful chunks it found and returns them. In short, the function asks the question in multiple ways so it can retrieve better and more complete information from the PDF. Rerank context. This function takes all the text chunks found earlier and rechecks how relevant each one is to the user's question. It does this using a special model called Reranker, which scores each chunk based on how well it matches the query. After scoring, it sorts all these chunks from the most relevant to least relevant and then returns only the top best matching chunks. In simple words, it picks the most useful pieces of text for answering the question. Running the application. Before setting up, make sure you have installed Ollama and relevant models in your system. In this app, we are using the model DeepSeek R1 1.5b. Here I am using UV to run this app. Make sure you have installed UV. I have shared the code in the description box. To set up this application, first clone the GitHub repo. Once you clone the repo, then run the command UV sync, which reads the project configuration, creates a virtual environment, and install all the required dependencies without you manually installing anything. Once the environment is ready, you can run the application using the command uv run streamlit run main.py. Here I am using Python version 3.13. I faced a few library conflicts, that's why I am using Python version 3.13. Now we can see the application in the browser. So that's all about today's video. If you found this helpful, please consider to like and subscribe the channel. Thank you for watching and see you in the next video.